Just out of curiosity, I mean, it's easy for me to figure out who's faculty, but how many postdocs and graduate students do we have here? Like, who's grad student?
Yeah, so I guess all the grad students are in the back right now. Not.
And postdocs?
He's saying their own. That's how I.
Yeah, and then we're all postdocs here. I guess Robert will probably also be coming. He's a postdoc. But oh, okay. Yeah, we have a couple other postdocs who are not here, right? Like they're not on right now. And then I think we have more grad students, but there's already a good number of grad. Jen is here. Yeah, okay. Yeah, so we can wait for Jen.
It seems like there was some pizza before, right?
This has been here. I feel like I saw this the past couple of times we were here.
Okay.
Back in the day, I'm told that this used to be like a pizza lunch deal, but then since COVID, I guess they stopped it. Yeah. Unfortunate.
So, was the pizza before the seminar or after the seminar? It was before. So like the speaker would have a pizza slice and talk in the meantime.
Yeah. Ah, okay. Nice. Right? It's kind of like at Stanford, they would have like wine and cheese, and the speaker would like, you could even drink the wine while you were giving the talk.
That sounds good too.
Longer.
Maybe a little. Yeah, I actually never thought about it, but this actually might be taller than me too.
Yeah, it is.
That's kind of disappointing. Yeah, by a stick.
We're not meeting the minimum requirement.
You think we might as well start? All right, yeah, we can start and then people can catch up. Yeah, so this is Dawid. He's visiting us from Maryland, where he's a student at Anson Book, and I believe you're like about to finish, like starting to apply for postdoc and stuff. Yeah, so he's going to tell us today about a solution to the coincidence problem.
Okay, so thank you for the very nice introduction, and happy to be here. So yes, I'm going to talk about the recent project I've been doing with Anson, and we're going to put out a paper roughly in a month or two. Here's why I was pretty confident with this one here, but not really with what the heck is this. And as Sarek said, we are attempting to solve the fact that baryon energy baryon and dark matter densities are very close in magnitude by in the dynamical way without really assuming what the dark matter mass is. Let's start from the beginning. So, well, basically, we know that dark matter makes up the most of matter in the universe, and this ratio is constant in time because baryons and dark matter redshift as a -3. So normally when we try to come up with explanation of what dark matter is, we try to come up with a mechanism that produces the right abundance. But most of the times we're not really thinking about why these two numbers are so close. And the reason why it is potentially interesting problem to tackle is that when we have dark matter mechanisms, for example, production mechanisms, for example, for accents, we predict wide range of like possible dark matter abundances. And similarly for baryons, the energy density is controlled by confining scale of QCD, which is exponentially sensitive to UV parameters due to dimensional transmutation. So just based on these two factors, you can easily imagine that the proton mass could be wildly different by many orders of magnitude than it is today. Or the dark matter could produce much more dark matter or much less, which means that we could think that it would be equally likely to have maybe 1% dark matter and 99% of standard model content, or the other way around. And the fact that we have these numbers to be within a factor of 5 seems like win on the lottery, essentially. So the typical way people try to explain this is either to invoke anthropics or make the number densities of dark matter or baryons to be roughly the same. And this could be done basically in two ways, either by having mirror symmetry when you have a standard model and its exact copy. And then you can also, when you have equal dark matter and baryon abundances, number densities, then you need to have the masses of dark matter and baryons to be roughly the same to explain the factor of 5. So the mirror scenario kind of deals with this automatically. Additional way we can try to tackle this problem is to share the baryon asymmetry between dark matter and baryons. And then you have to, subsequently, you have to come up with a way to explain why these masses are roughly the same. And there have historically been two approaches that tackle this. It was either using coupled CFTs or recently unification. But the bottom line with this approach is that it only works if your dark matter is of order GeV. So we are trying to come up with a way that wouldn't rely on this small band. And in principle, we could make this happen for arbitrary masses of dark matter. So pictorially, we could imagine a situation when in the early universe, the baryon energy density is vastly different than the dark matter energy density. Like, let's go crazy and say it's like 5 orders of magnitude. And then this mechanism starts working, and at late times, they finally are comparable.
This was tried before with dark energy, right? In terms of the tracker field.
Mm-hmm.
So you start with arbitrary amount and then you forward for that tracker.
Mm-hmm.
So this mechanism is not going to be a production mechanism for dark.
No. So yeah, it's not production. It's more like, in this case, you say you underproduce dark matter. How do we get energy density of dark matter and baryon to be the same? So on top of that, I'm going to get to this, but you assume that you already produced baryons and you produce dark matter, and now you're try to equilibrate later on. So it's not necessarily related to the dark matter production mechanism.
Well, I guess could I start with the 0 dark matter and then this is
You need some. So the whole. So it's going to get obvious later on. Okay. So So basically, for the rest of the talk, I'm first going to just talk about bare bones of the mechanism. How does it operate? And then I'm going to add a few more elements to actually make it feasible in the real life situation, and then show you example of parameters that end up working. And finally, I'll talk about how this parameter is constrained and what possible signals it can generate in experiments. So basically, the way we do it is to introduce a scalar that controls the mass of baryons and dark matter. And let's say in the early universe, the baryon mass is much larger than, the proton mass is much larger than today. And the scalar is, say, frozen. And then it starts rolling down the potential and oscillates around the minimum, which sets the value of the proton mass today. And for the dark matter mass, we get the opposite effect when we increase the mass of dark matter, so that like these two energy densities meet that when they're roughly the same. What? So this is an example of how the thing could evolve, essentially. It's just like, I'm just saying that the only thing that we need is that the masses go in the opposite direction. So if you increase the mass of the baryon, decrease the mass of dark matter. And so if we want to think in terms of potential, what we need to, so the situation that we need is that the finite density effects are the dominant thing. So we need baryons and dark matter that are non-relativistic. So we need a period in the early universe when this finite density effects are actually driving the evolution of this field. And we need to have, and we already have to have non-relativistic baryons and non-relativistic dark matter for this potential to actually make sense. So then if we, I'm going to explain on the next slide how we do it, but if we change the mass of the protons and scalars exponentially with the value of the field, we can work out that this potential is minimized when the ratio of these coefficients in the exponent is, so the ratio of energy densities is the ratio of these coefficients, which we naturally expect to be roughly the same, given the order one ratio at the minimum. So pictorially, it means that if say initially the baryon energy density is much larger, we probably would start here, and we want to end up in this point. So if this potential is true, eventually we're just going to end up oscillating around this minimum where energy densities are roughly the same.
Is this the only dependence on phi? No.
I'm gonna go more into detail on that. How we make this like the dominant thing at some point in the early, but there are other contributions.
I mean, does it have its own proper mass balance, self-interaction?
In
the absence of, because if I said ND and NDM equal to 0, I have just a phi potential.
Yes, exactly. So you need, so the thing is that you need to produce baryons and you need to produce dark matter before. Like you need to have non-zero number densities of both.
What Keith was saying, suppose there are no baryons or dark matter altogether, if you take a loop of the whatever particles, do you get the self-interaction?
Oh,
Not attached to anything.
oh yeah, like, so it's gonna get obvious in a few slides, okay? Like, yeah, you get vacuum potential for this. You don't need you don't need this finite density thing. There is a vacuum potential, but just suppressed. So from EFT perspective, like we can get this exponential dependence on the mass by linearly coupling the scalar to to QCD and some dark gauge sector. And this way, we are shifting the value of strong coupling. And if we remember from the dimensional transmutation, we're going to change confining scale by this exponential factor. So basically, so the lambda QCD is exponentially sensitive to value of the field. And since the proton mass is proportional to confinement scale, we're exponentially changing the proton mass. And then similarly for dark matter, if this is, we can say it's ALP, which mass depends on the confining scale of this dark sector, we can do the similar thing. But what we actually require to change these masses in opposite directions is to have the relative minus sign between these in these couplings.
My next question, so now when are you doing this? Does this happen very early on?
Yeah, this has to happen before BBN. But we still need to require that. So I'm gonna explain how we like managing to meet all these conditions that protons are non-relativistic, and we still finish before BBN.
And then phi is fixed.
Like initially phi, yes. So phi is fixed, and then we as it rolls down, we're going to
No, but it's fixed before BBM, so.
Yes, exactly. It's fixed before BBM. Yes. But I'm gonna get to that. So to quickly go through, so we solved this vacuum potential problem by using Z symmetry, by having n copies of the standard model in dark sector. We had we had a similar construction previously in the paper when we did it for by structure constant, but basically the idea is that if you have a potential that's periodic, and you add up and cosines, the leading contribution to this potential will require n insertions of the cosine, so you can exponentially suppress it and make this contribution very small. So that's how we are controlling. But if you want more details, we can chat about this later. But now let's come back to how the field actually behaves. So supposedly we started a situation with baryon energy density is much greater than dark matter energy density, which factorially means that we start roughly here where this red dot is. Then our evolution equation is only going to care about the baryon term. So only this plus exponential, the minus one is relevant at this stage. And to understand how the field behaves, when we start the whole story, we need to know how big is the mass of this mass of the field at this specific point. So we're going to have two distinct situations. If the mass is much smaller than the Hubble at this time, the field initially would be frozen. If the mass is much greater than Hubble, the field will oscillate right away, and we'll get different phenomenologies for these two regimes. So the first one, we kind of call it pseudo slow roll, is when the mass is much smaller than the Hubble. So initially, let's say we're starting at like on this right side of the plot, which basically means that our lambda QCD is much greater than the value today. And once the mass becomes of order Hubble, the field starts slowly rolling. And we call it pseudo slow roll because second derivative is actually also important as opposed to the normal slow roll. And as the field rolls down and reaches the minimum, its kinetic energy is pretty small and undergoes small oscillations from then. So once you roll down to the minimum, the value of lambda QCD will not change a lot. Whereas the opposite scenario, I'm going to get more into detail, like how this actually goes. Whereas the opposite scenario is when the field starts wildly oscillating right away. And the potential problem with this is that we start at a very high value of lambda QCD, and then we dive down way below the current value of lambda QCD, which can potentially make protons relativistic. And it violates our assumption that protons are non-relativistic. So in other words, it makes things a little bit harder to control and gives us less freedom to set initial conditions. So we're going to skip completely this scenario and focus on the pseudo slow roll because it allows us to start with very high values of proton mass, making this non-relativistic assumption even easier to satisfy. And then when we slow roll, we're not going to shoot too far away from the current value.
I'm still not clear what scale you're doing this at. What is the mass of phi when either in this picture or the other picture when you start to roll?
The mass of the phi.
You're talking about protons, so I assume now you're doing this after the QCD transition.
Yes.
Otherwise, there's no proton. Right? So,
yeah.
So there's not a whole lot of space in here.
Yes, exactly. So okay. So exactly. So So basically, we'll have to consider other cosmology to make it happen. Well, I'm going to actually explain. So yeah, so if pion, like obviously pions are going to be a problem. Pion contribution to this potential is going to be a problem, and so if it was just, but I'm going to go into more detail because there's additional thing that basically makes it even more dangerous than pions. That is because pions are at below certain temperature, but below 10 MeV roughly, they are no longer dangerous. But there's another contribution that is still dangerous there. So,
are you also worried about the fact that your lambda is dropping sizably after QCD phase transition, and that's presumably dumping some amount of entropy in the bath before BDF? I mean, is that an issue? Also related, are the number densities assumed to be equal to big NF, or for the baryons on dark matter?
No, they're completely unrelated.
So far you've only talked about the evolution of the mass, but you've said that you imagine that you've produced dark matter and baryons prior.
Yeah.
So what are the number densities that you're coming in?
So basically all we care about for dark matter is what the energy density is. We don't really care about what the mass of the number.
Yeah, but you're only telling me about the masses of dark matter in the baryons, right?
Yeah, I'm saying that that's where we control.
Yeah, so then what are you assuming about the number densities?
So the whole thing is that we don't have to assume anything about number density of dark matter. We're saying we're changing mass, but I didn't say what the mass was to begin with. It's like
where it will go probably. So
yeah.
Attract the point that is regulated by the energy density. So there will be some insensitivity to the initial condition in terms of the numbers.
But the number densities.
Yes,
Oh,
but
so
like
you just say okay, the number densities are what they are, whatever.
Yeah, so like exactly.
That's what they
Okay.
But how big is your lambda QCD in the early universe?
So the point that we're gonna so the point I'm gonna show is gonna be 10 GeV, so 100 times bigger.
That's all.
Yeah. So this is the point where you still are not you're still not messing up the Higgs this way.
That was my next question.
Yeah. But actually it may not be a problem, but if I get but this is going to be more obvious later, what we are actually doing. Okay, so to summarize, we have basically two types of motion that can happen. And one when the field will just oscillate crazy like this and potentially make protons relativistic. We don't want that. So we focus on scenario when the field will slowly roll and then oscillate a little bit around the minimum, making like once it rolls down, making the mass of the proton roughly 1 GeV. But now let's actually dive a little bit more and to see how see more clearly how the field evolves, like where the scalings of proton mass and other important quantities. So the first phase is like pretty trivial. At this point, the mass term is much smaller than Hubble. So however, whatever was your initial condition for phi, the field is frozen, nothing interesting happens. But once we get to the point where the mass term becomes important, I think I jumped a little bit too far. Okay. So once the mass becomes important, then the field will start rolling slowly here, and this roll will be proportional to log of time. And just from this, we can figure out like how the mass of the proton is going to change. So we know that because it's log of time, this part is going to scale as T2 minus 2. So we know that this thing as a whole also has to scale this way. And because this thing is non-relativistic, we can work out that this exponent is going to scale as a to minus 1, or the temperature. So in other words, because it controls the mass of the proton is proportional to this exponent, we know that the mass of the proton is going to scale with temperature when the field rolls down around here.
Yeah, let's give again about the self interaction. You explain something there with that the groups somehow between different sectors cancel out. But there is also a vacuum condensate of the theta of UCD fields and so on. Presumably only our sector is hot, right? So there's gotta be some temperature dependent mass to the as well, right? Just G mu squared is not 0. G mu squared is not 0. So there are all this wonderful UCD condensates that belong.
Yeah, so I'll get to that later. So
because this is the baryons are still present in the small numbers. And
you're talking about the thermal contribution, right? To the
right?
yes. So I'll get how okay. I agree that if we were just to keep like normal cosmology, the thermal contribution actually is more important than this effect. So we have to go around this problem, and I'll explain how we do it later.
I'm still puzzled with the scale. So you're saying if that's your equation of motion, you have no additional m squared phi. There's no bare mass for phi.
So at this case, like this moment in time, it's not important. So yeah, the spoiler alert is that finally we want the field to fall into some vacuum potential, to some bare mass term.
But again, it's still a question of scales. So, but that mass is presumably larger than an MeV, right?
Of the scalar.
Yeah.
Probably wider, much
It's-
wider.
yes.
So
But then
it's some sort of
And is it there? Is it present in the thermal bath? I would guess so.
no, it's not excited. The couplings has to be rather small. It's more quintessence like, right? So the coupling is very small. The expectation value, I suppose, of this phi is very large. That's and
So there's no thermal background.
there is no thermal background, or at least you have to make sure that the thermal background is small. So it's more along the lines of Polikov, Damour, Northweb constructions, where the mass is a slowly varying function of some
How big is that?
some rolling field.
What is the size of that?
So like for F over CB is going to be 10 to 12 GB.
Let's decouple.
So C over F is C over F is no, not C, 1 over F, right? It's 10 minus 12.
No, C over F is 10 to
Okay.
10 to minus 12.
Can I ask one quick question?
Yeah.
I guess there is two contributions to the phi potential. The one is the one that you mentioned, which is attributed to the number density of the baryon dark matter. The other one is like phi coupled to the GT field here. So yes, but then in the end, you're gonna have some parabolic potential with the wiggle over it. But you want to have this phi in the end, see that I guess the origin of the system. So my question is, if you have such a wiggle, and then don't you have to be worried about like it's being
To displace from
sitting at some other place other than
yeah. So well, in fact, I'll get to that later. But we're going to have wiggles, and we're just gonna have large amount of wiggles, so that it doesn't really matter. Like the space. Yeah, it doesn't matter because the spacing between the wiggles is so small that you don't change mass of the proton that much. So the thing is that you don't want to like sit right at the minimum. We can solve problem a little bit imprecisely, right? I mean, we're not really baryon rho dark matter is not exactly 5. It's some number. Like as long as you are qualitatively within like this factor of 1. Like order 1 from this final value, you're fine in that sense. So basically, I mean, if you have a lot of wiggles and they're close by, and you're not shifting the mass by a large number if you fall into the wrong one, then you're good. You still qualitatively solve the problem.
You said you don't get there.
I'm gonna get there, yeah. Okay, so the next thing here is that we can use the result that we found that this mass changes with temperature to figure out exactly what's the trajectory of the field when it goes in this, when undergoes this pseudo slow roll. And it turns out that if we make this change of variables input into equations of motion and look for the static solution, because we expect this thing to not change like at this particular moment, we find that the trajectory that field actually follows is where the mass of the field and Hubble are equal. And it's actually important result because it means that whatever your initial misalignment value, all your possible options are going to end up at a minimum at the same time, at the same temperature. So in other words, this this solution is like very, very generic. It doesn't depend on the initial conditions. The only thing that controls when you roll into the minimum is this C over F. But in terms of like what's your as long as you are in this regime when the field is slowly rolling, then it doesn't really matter. So to summarize, we have like three important results from this part to remember. So the one is that the mass of the baryon is inversely proportional to the scale factor, which implies that that's something I forgot to say. The baryon energy density goes as radiation in this time, and this is what allows us to actually make this adjustment. We're making baryons drop faster so that they can finally get onto the trajectory that we see today.
So they are on the track.
Yes. Yeah. Mm-hmm. Yeah. And finally, the field follows this trajectory. So, and then the third stage is where the field falls into this minimum and undergoes small oscillations. Then we can use adiabatic invariant to figure out how the energy density of the field changes. And since the mass, this current mass is some linear combination of baryon and dark matter number densities, this is going to scale as a to minus third. And when we work out what the energy density scaling is, we see that this is a to minus 4.5, which is faster than radiation. So now to summarize, like all these three steps, let's make comparison between how the field evolves and how energy density changes. So initially, the field is frozen, and the mass of the proton is much larger than it is today, and it's non-relativistic, so it's going to redshift at a to minus 3. Then once the slow roll period happens, the baryon energy density goes as a to the minus 4, and then the field will slowly oscillate. I mean, it will do small oscillations around the minimum, making like the mass of the proton not change by a lot, which means that this will again redshift at matter. So the one final question is, does the scalar overclose the universe? And so the way we can work it out is to see that in the slower regime, when the field goes as logarithmic time, the energy density of this field will also scale as radiations as baryons. So in other words, their ratio is going to be fixed. Now the question is what the value of this ratio is. And we can use the result that we found before, that what the trajectory of the field is, that the mass equals Hubble. And from this, we can work out that this ratio is actually less than 1/2. So in other words, once the field rolls into the minimum, we know that its energy is subdominant to energy density of baryons and energy density of dark matter. And if it would continue oscillating like this, it's just at some point, this energy will not be relevant at all.
So you can't make 5 at dark. Or what's that?
I'm gonna get to, well, that's if it would continue like this, but eventually you're actually going to fall into the vacuum potential, so the mass is going to get fixed. So it's going to be some subcomponent of dark matter. And to jump things forward, the case I'm going to show is going to be like 1% of dark matter. Okay, so that's the end of the toy model section. Now let's see how to make this thing realistic. And basically we have 2 important challenges that we have to overcome to make this thing realistic. The first one is that, well, we have finite density effects today. So like this potential that we saw was still the one that rules the evolution of the field today. The mass of the proton on Earth will be vastly different than elsewhere. And the second thing is something that we, I guess, discussed in a lot before. So this is also like another step that we have to address. So to summarize, for the macroscopic objects, basically the problem is that, as I said, the the number densities of baryons and dark matter, or at least the ratios, are going to be vastly different in vacuum than inside a dense object, which pictorially means that we're shifting the minimum of this potential way to the left, making protons much, much lighter on Earth. So in order to fix this, we need a vacuum potential. And we're just taking potential of this form. So, and as I said before, then the field will redshift as the dark matter, but we are guaranteed already by the previous calculations that this is going to be some subcomponent. So pictorially, we imagine that initially the field rolls in a smooth potential, and then will fall into the closest vacuum of this new of this vacuum potential, and just stay there. So we're not aiming to like exact what.
So in this arbitrary small vacuum, there will be a linear coupling between the parts.
Exactly. Yes.
Yeah. So what is the size of it?
Well, so
Is it a fifth force?
yeah, it's a fifth force. So I mean, I'm gonna get that at the very end of the talk. But basically, the mass is 3 eV for the point that we're considering. So we're on the edge of fifth force and stellar constraints there. But basically, the strength is going to be controlled by this strength of the interaction. Well, I mean, I'll get there. So in order to clean this, we need to make sure that we are not changing proton mass substantially inside a neutron star. So this is our benchmark. We just want to height of the barrier to make sure that the proton mass does not change significantly inside the neutron star. Okay. Now the second thing is the fact that once we have coupling to gluons, we're going to generate coupling to photons. And we can make some quick order of magnitude estimate of like how big this coupling is. And we can, since we are below confinement scale, we can do it by RG evolving through confinement. And the most important contribution comes when we transition from free flavor physics to pion chem physics.
Wait, the like wiggles that you were getting before, is that supposed to be coming from these G squared couplings, or that's you put?
No. This goes from vacuum potential.
Like you couple it, you give it some like GG dual coupling to some like gauge group like that. We have like cosine potential.
Just write it down.
Right.
Just write it down.
Yeah.
It's
Okay,
just-
but
Yeah.
but in
I mean-
principle, that would be one way to get it.
A science engineering.
Yeah.
You just wrote it down, but yeah, you're right.
Yeah, that's one way you
You probably do it.
So like when we estimate how how this field changes the ENM alpha, we see that this, by RGA volume, we see that this main contribution is proportional to the difference between beta functions when we change between free flavors and ion kaons. And we look at PCD, and since PCD is exponentially sensitive to the field, we get this linear coupling. And finally, we see that this coupling to photons is going to be comparable to the coupling to gluons.
So this is the problem of as the solution in the Higgs literature, right? Is how the way Higgs couples to photons is not going to be unrelated. Like in the good old days, like people discuss things on doing the couplings to photons at that point.
Yeah, what I'm trying to say is that like thermal contribution from electrons is killing you, essentially.
I'm just talking about the coupling to F mu squared probably can be lifted off the Higgs literature without excluding lines. Look into the right place, you can read it off. That's what I'm saying.
Okay.
Yeah, Higgs time.
Well, not completely. They have some bugs there. If you look into some research paper with nitrogen, then not so bad.
Okay, based on what we have, then we generate like through thermal through ENM corrections to the thermal contribution from electrons, we generate contribution that's like 10⁻⁶ times standard model energy density. So, and we want the baryon contribution to be more important than this. But we're already losing on the grounds of asymmetry. So once we do a plot, we would like the baryon energy density to be more important than this thing. But we see that this never happened before 1 MeV, essentially. So the way we go around this problem is to do entropy dump with relativistic scalar. And we make it decay into Higgs and make it heavy enough so that it's not detected colliders. So what it ends up doing is that the early decays of the scalar, once the early decays of the scalar make the standard model redshift slower at a to -1. So eventually, when the reheat happens, it's when these two lines intersect and standard model takes over. And this
It's a different scale.
yeah, it's a different scalar. We just say yeah, it's some relativistic scalar.
Are you sensitive to the amount of energy you put in?
What do you mean?
Oh, you want to dump some entropy and so on. Are you sensitive to how much you do? Does it have to be carefully engineered or not?
No, I mean coupling is pretty small. It's like 10 to -8 GeV. So
How much energy I dump, right? It's a free parameter. Does it
Yeah.
have to be adjusted carefully? Okay.
Yeah, so here we are. Okay, so here we're taking the maximal approach that like you basically you're getting this 10 to -10 factor from this entropy dump. I'm gonna show you what's our initial assumption for baryons. But basically, okay, when we draw a baryon line, we see that if we would just keep the scaling, the baryons would eventually, if we go back in time, would eventually dominate over the standard model. And so this is the sort of situation that we have today. The non-relative, like the baryon density is much greater than CMB. And also this this hierarchy was shown to be possible in Aflatoxin baryogenesis. So we take inspiration from that at with right model, we could get these initial conditions. So this way we can always, like, we can make sure that the standard model radiation is subdominant to the baryon energy density. Okay, so now let's take a look at the example. So as I said before, our F over C is 10 to 12 GeV. In this case, we're taking the ratio of C's to be 5. It doesn't have to be exact. It doesn't have to be 5 to solve the problem. We chose it to be 5. The F that's associated with the vacuum potential is 10 to the 4, 10 to the 5 GeV, and the potential barrier is a 10 MeV. We take the reheat temperature to be 1 MeV, and finally we're adjusting. So initial ratio between dark matter and baryon is 1/50, and you want to get to the 5. So we're adjusting energy densities by a factor of 250, the ratio. And the proton mass is 100 GeV initially. So let's look at every stage separately. So the first important scale is when the field starts rolling. I defined scale factor to be 1 when the reheat happens. So in other words, the scalar starts rolling 7 decades before the reheat. And then the energy density of the scalar like dominates over anything else. Baryons have much greater energy density than standard model. And so far, since we started, like still nothing is set. We start at like higher values of the proton mass and smaller density of dark matter. Then 2 decades later, because remember the baryon mass scales with temperature. So if we want to adjust, we want to lower the mass of the baryon by a factor of 100, we have to wait 2 decades for the field to roll down to the minimum. So this is when it happens. And still here, the baryon energy density is more important than the standard model. So at this point, we don't have to worry about any thermal contribution from it. But we have already set the proton mass to be roughly 1 GeV and the ratio to be close to the 5. Then the vacuum potential becomes important. I denote that by A0, and the standard model path becomes comparable to the baryon energy density. But this thing happens slightly before the baryon contribution is like by say a factor of 1.2 or something for this particular data point. So I just took them at the same time. And that's why I wrote that the standard model energy density is the same as the baryon. And also, since I took lambda naught to be 10 MeV, lambda naught to the 4th is also equals rho standard model. And that's a benchmark because we're saying that the field will roll down into the minimum once the kinetic energy of the field is smaller than the barrier height. So that's why it's a benchmark for, like, it's a point for this potential actually starting to work. And once this happens, we are basically setting our ratios and proton mass in stone. So from now on, nothing else can change it. And finally, 4 decades later, we the standard model or the reheat completes, and we come back to our regular story.
What's the change in entropy?
In entropy?
Well, through this reheating, so you dumped entropy.
Mm-hmm.
How by what factor did the entropy change?
Yeah, I don't remember the number top of my head, but I can double check it later and we can come back to this.
But is it 10 or 10 to the 10?
No, this is not a big number.
So, sorry, can you go back to the number? So it's. I'm not sure if it's just for the numbers that you chose, but how crucial is it that, I mean, this new heavy phi thing is decaying like right before BBM such that the standard model bath temperature is not scaling like 8 to the 4th yet.
So it all has to do, well, with the barrier height that you can choose, because
Sorry, let me rephrase in a better way. I think, yeah, you set things up here so that the reading is like right at 1 MeV.
yeah, so maybe, okay,
Can you push that
maybe
back?
let's wait until the very end. It's going to be obvious in the parameter space plot.
Okay.
Yeah, so the final thing is to talk about what this data point is sensitive to, or like it could be excluded by. And the first thing is what Maxim pointed out before, is we generate linear coupling, and we have fifth force constraints, and we have cooling constraints that this field is sensitive to. So we're living at the edge where the stellar constraints and fifth force can detect it. And finally, we can have late, because of the coupling to photons, we can have late decays that could basically make us see light like going at us from everywhere in the sky, because this thing is order EV, so it's literally close to optical. But it turns out that if we look at the bounds for this particular mass and we translate them to like this particular coupling and take into account that just 1% dark matter and not 100%, we get the bound to be 10 to the 10 GeV, which is 2 orders of magnitude safe compared to the point that we chosen. And then finally, the thing that we have to worry about with the vacuum potential is the fact that when we are rolling down, we are actually going over hoops. And the problem with this is that it can happen that for a specific choice of parameters, these oscillations are going to destabilize quantum fluctuations and make them get exponentially enhanced. And when it happens, they can back react on the homogeneous mode and slow the field down way before it gets a chance to get to the minimum. So this problem has been worked out in terms of relaxion 3 years ago, and we basically took their the timescale for the process that they figured out to make sure that this timescale is long enough so that our field can roll down to the minimum without causing any problems. And when we take all these things into account, here's the parameter space. So this red point is the point I've chosen. It's right above EP, sorry, the fifth force constraints and the stellar constraints. And this parametric resonance requirement is kind of cutting off a lot of parameter space here. But it is not like, it's not as bad as it looks. It's just a consequence of using the vacuum potential. If we, for example, generate late potential by GG dual coupling, then we can turn on this potential after the thing rolls down into the minimum and basically open a huge chunk of parameter space here. So it's not really a problem. It's just more like how this particular choice of potential affects the parameter space. And this is mainly the reason why for this particular setup, we had to choose a low reheat temperature, because if we want a little bit higher to 10 MeV, we are forced to use higher barriers so that the field falls into the minimum before thermal BAP becomes important. So again, this example could work well if we would use GG dual coupling to generate vacuum potential. We could open this up. But even on these grounds, because these are still working constraints, the question like how much, to what number we actually trust them, or the actual error bars. This is like factor of 3 away from this bound. So you could say that technically it is in tension with these bounds here. Okay. So that basically brings me to the summary part of the talk. And so the key takeaway is that the fact that dark matter and baryon energy densities are so close together seems to be a win of the lottery. And currently, models that address that problem require the mass of dark matter to be about a GeV. So we've shown a dynamical way to do it without assuming anything about dark matter mass. So in principle, you can apply it to your favorite axiom model and see how it works. We're currently working on the QCD axiom case, and yes, it would be nice to see if people like it. Anyways, thank you.
So there was this like right before the reheating happens, there's this important thing, which is that your heavy phi is pumping entropy into the central bath, but the baryons energy density, you're still assuming the scaling like (8⁻�3). So how are the baryons decoupled kinetically from the center model bath? Because
they don't decouple. We're just saying. So the thing is that the standard model, well, maybe this is not correct terming. It's basically, it tells you what the kinetic energy of the protons is, or like baryons is at this point. So it's more of a control like how energetic protons are. Because the thing is that like you have
okay, sorry,
yeah.
sorry. Yeah. Anyway. But there's still
You see the axis, so then you have a low reheat temperatures. Is this affects how you generate the baryon number density and dark matter density? So is that why you're doing the QCD axiom now? So you're relying on some misalignment mechanism?
So so for the you're talking about the so in this case for the QCD axiom, like the idea is that you're not changing proton mass by a lot, because the coupling of protons to axions can change it by maybe like 50 MeV or something. So it's more like you can only change the dark matter mass significantly. So for this case, you can make the dark matter do the heavy lifting. In this case, when we had a ratio of 5, when the baryon energy density scales as 8⁻⁴, the dark matter scales as 2.8. So basically doesn't move much from this matter scaling. So all the like for this particular choice of C's, the baryons are doing the heavy lifting here.
But for the axiom, it'd be the other way around.
Yeah, it would be the other way around. It's a little bit. We're not exactly sure if it's actually going to work. So it's still work in progress here, but that's like the base of the idea.
Do you have to have a much larger baryon actually than usual? Because these spots don't think about that.
Yes, that's the basically you're generating a lot of so basically now you're saying that your baryogenesis is super efficient, and now you're getting what?
That's what I asked him. I said, is it a factor of 10 or is it a factor of 10?
Yeah. I mean, that's really, really hard. Like what? Yeah, sorry. Maybe your.
No, he said it was small, but I still don't have a feeling for the scales. You have 2 phi's, right? So what is the rho phi for each of them, say, around an MEV?
Around an MEV. So at MEV, the rho of the big phi, it's going to be the rho of the standard model at this time, because this is like when you reheat, like for this particular data point.
Yeah.
But for the small phi, this has to be smaller than the baryon density at this time. Baryon energy density at this time, because we're bounded to like from previous calculations, I showed that the phi energy density is not bigger than 1/2 of this thing. And then you have a period when this reaches (10⁻⁴), and then it goes less as matter. So it's going to be less than
So,
that.
but the big phi you're saying is not much bigger than the energy density in the radiation that's there already.
Yeah.
So the entropy jump is about effective too.
Yeah. Yeah, that's sort of how I roughly remember. So.
Can I ask one technical question? So if you go back to the previous slides where you display the targeted primary space. Yeah, so why larger phi gives you more transmutations? So this is coming from the preventing the fragmentation.
Yes.
How the HFT wiggle, right?
Yeah.
So I would naively guess like larger phi will give you the stronger Solomon friction.
Larger phi,
Larger F. Yeah.
larger F.
Yeah, larger F will gonna give you the stronger Solomon friction. So right, I guess the parameters we can know weaker.
Which one over that?
Oh yeah, weaker. Sorry, yeah.
Mhm.
So then you're in less dangerous situation, I guess. So why?
You're saying that
Why
large.
that is not consistent with you're wishing that you don't want to have current human.
Because if you make F really big, why do you have parametric resonance at all? Because the couplings are very small.
I think it'd be opposite way. If you have very small.
If you want to go this way.
Well, there's two F's. Which is what we call
little.
it?
And the app in
The vertical. You're talking about the vertical.
Why is that a problem?
this app is the digit constant, right? This
So-
whole app is digit constant, right?
It's a big, but this F, so the problem with this F, it tells you when the,
I mean, as you have larger app, you're gonna have smaller effective current units, right? So why do you have to worry about the primary space where you have larger app? You don't have current units there.
Wait, the F appearing in the cosine potential
This is the big F.
it's a capital.
it's a big F.
Well, I don't know, maybe you can go back so we can see it.
Those,
Do you have the cosine potential written?
So it should be named. Yes.
Yeah.
Okay, sorry.
Because several times talk about parametric resonance
Mhm.
experiments. So our GPU potential of your job and why do you work on the GPU? Of your background.
So it's more, I would say that we may end up doing that. It's more the case that this is additional thing that you have to add. I don't know, it was more like initially it was more like aesthetic preference. That was nicer to work with vacuum potential that doesn't turn on. But then it seems like it might be better just to apply it this way. But okay, there's one other thing that you can actually do. It's probably the thing is that we're a little bit too strict in this low MEV regime in terms of requiring that you have to be greater than the baryon energy density, simply because the pions are no longer that dangerous. So it's very likely that you can just reach the read temperature 5 without paying any penalty and keep the same parameter space plot. So in that sense, I would say the story is not finished yet, but we previously considered GD dual. It was more like a option that this entropy dump was opening the option to use the vacuum potential. So I would say it's more like aesthetics rather than anything else.
Another question is, in principle, I'm trying to enlarge the well-motivated dark matter boundary space. So what's the mass range that your model accommodate for that?
For dark matter?
Yes.
Because of course, I have the scalar potential and tuner mass one is but I assume it's a linear potential and there's RG effect involved. The tunability range is still very fine. I still can comment on how much we are or normal wave story, maybe natural.
You don't care about the mass, right?
Yeah,
It's just the density, so you need to know, for any given mass, you just have to have the right production.
But the scalar potential is adjusting the dark matter mass, right? It's not arbitrarily adjustable. It's a
so for example, here you're like for this particular parameter point, you're not adjusting dark matter mass by much.
Right.
You're adjusting the proton mass by a factor of 100, you're adjusting dark matter by 2.5 here. So it's not a lot, but you could in principle also get it to work with smaller ratio when the dark matter mass can do a little.
I'm not talking about the dark matter mass change. I'm talking about what I provide the mechanism to produce dark matter valuing vectors for dark matter of mass, GeV, TeV, or MEV scale. What's the at the first glance, of course, it seems like you're solving coincidence problem without detail dependent on what exactly the dark matter mass is.
Can you go back to the initial condition, please? And,
I have
AI, maybe it was okay, so you're, this rho dm equaling rho d over 50. What if I made it 10 to the rho d over 10 to the 5? What would happen?
So it's more about if you're comfortable going for to higher masses of a proton, essentially. Because so the thing is that with this entropy doubt, we should be fine with having higher masses of a proton.
Wouldn't it be safer to play with dark matter than with protons, right?
Yes, but the thing, yeah.
Yeah,
that's safer, but the problem is that you're reversing the pendulum, so to speak. Like so if you want to, for example, have a cease to be 1, then you're changing dark matter by the same amount and baryon by the same amount, and you want to use the slow roll solution. Then the problem is that the slow roll works too well, and you don't have enough kinetic energy to go to this factor of 5. You can go to factor 1.5 or something. So in that sense, unless you want to be tuned, you want to live where on the side where baryons are doing the heavy lifting.
Just creating different initial conditions for other initial conditions. The standard picture, okay, the baryons are whatever they are. Right? You have the baryon symmetry, you have the baryon density. Now you say you want to get the density of dark matter to be 5 times bigger. So normal thing, you pick your dark matter mass, and now you have to arrange it so that the initial density of dark matter, when it's in equilibrium, has a certain density, a certain ratio. Aren't you just trading that number for some other numbers? I mean, I can't start, if you could start with these things being arbitrary and you always end up in the same thing, right, that would be one thing. But if you're having to set different parameters initially so that you get the right answer at the end, I don't really see why that's different from the standard.
In your toy model, you did have a big ratio between the number density, right? That's okay.
Yeah.
But you're saying in the realistic model, you don't.
Well, you could probably crank this up to be smaller, like this number to be smaller than it is.
Yeah, that's what the point.
Yeah,
But
so in
you're
that,
coming at the expense of having to change something else, right?
That's why I asked her, maybe unless, away from the normal storm story, you can enable, PV dark matter easily. That's why I asked about the reasonable modeling and the target dark matter thing.
Like this scenario, this scenario works as long as you underproduce your dark matter. If you want to go the opposite direction, then you have to be very careful if you're not making protons relativistic.
But like even for these numbers,
Mhm.
can I really take the mass of the dark matter to be anything I want? Like, could I take the mass of the dark matter to be 10 to the minus 10 EV and just have a really high number density?
By the way, there's, at this initial scale, there's no proton, right? So you're above the QCD transition.
Well, the QCD scale of it.
It's fine. The QCD scale is also high.
But like, so I don't know. Are you getting the new QCD scale by affecting anti-aliasing scale through dimensional transmutation, or is
Yeah.
I think that's.
then that's still a logarithmic change. That's a finite range of how heavy the photon.
Yes. Yeah.
That actually tells you, people dark matter mass range. The dark matter mass cannot be more than IQ in this to be algorithm. That is RG of along. With whatever I start the dark matter mass with, like the proton mass is gonna drop by 2 orders of magnitude. Does that also mean the dark matter mass is gonna increase by 2 orders of magnitude?
No, because we picked the ratio of, like, for this particular example, we picked the ratio to be 5. Which means that if you change the proton mass by a factor of 100, you change dark matter mass by a factor of 2.5. Yeah, because it's like, basically look at the exponent. You have exponent 5 times some number and exponent with 1. Okay. In front. So like the proton gets a boost and it gets changed more than the matter.
Okay, but so then like for these numbers, I can end up with dark matter with the right abundance for almost any mass. Like this mechanism, these numbers.
Almost any has, but not any initial abundance.
Yeah. You need the right initial one.
Yeah, but that's what you need.
Well, I guess
It's
his original
a
motivation,
different initial abundance.
but his original motivation was like other solutions to the coincidence problem only work for like G mass range, whereas like this is a solution that works.
Well, I don't think it was a very specific value of the and that's it was like
You probably can show that similar quantities that you have very many low or low big large range. Cool. Yeah, there are no more questions. Thank you again. Nice talk.